else is there?
I think Martin Green also joined us.
Ah, okay. Prof. Martin, good evening. Prof. Usama, good evening. Prof. Quack from Singapore. Thank you for joining us. Ardent supporter of us. Thank you. About 30 people online. Before we start, I would like to request sorry. I'd like to request all our online participants to switch off their mic, mute their mics and their videos. It has happened the last few Isaac's series. We have intrusions that were not very welcome by the speakers. Camaro, as in Camaro of the CEO. Is he in?
I don't know whether that was Cameroon because they put it
Cameron, okay.
Cameroon, not taker. I don't know.
That's right. Note taker is
Yeah.
AI. Yeah.
So we wait for Brian to join us.
Yep.
Yeah. Brian will be the co-host, so he can share the slide.
Great.
Yeah.
Let me get my slide up. Um,
I'll let me start off with the introductions.
Yeah, I think probably you can start the introduction.
Yeah, all right. Okay, all right. Okay. Salam sejahtera, selamat pagi and a very good morning to all gathered here virtually. We are here for our International STEM and Innovation Colloquia Series 24. Thank you to Drs. Nazri Halif and Sharifah Nofaiza, as well as UNIMAP Vice Chancellor, Prof. Zaliman Sauli, and Deputy Vice Chancellor of Research and Innovation, Prof. Rizal Fandi, their respective officers and broadcast control team here led by Mr. Sharizan for hosting this event. I am Prabha, the moderator for this ISICS Series 24. Before we begin, as is normal, I would like to introduce our esteemed speaker for this Series 24, Prof. Brian Schmidt. We wish you a very good morning, Prof. Schmidt.
Good to be with everyone. And anyway, it is great to be able to give this talk. And I guess we're very punctual in Malaysia, 4 minutes early.
Almost. We are a bit early. Yeah. Okay. Brian Schmidt is a distinguished professor of astronomy and the 12th Vice Chancellor and President of the Australian National University from 2016 to 2023. Brian was raised in Montana and Alaska, USA, and received undergraduate degrees in physics and astronomy from the University of Arizona in 1989. Under the supervision of Robert Kirshner, he completed his astronomy master's degree in 92 and PhD in 93 from Harvard University. In 94, he and Nick Suntzeff formed the High Z SN Search team, a group of 20 astronomers on 5 continents who used distant exploding stars to trace the expansion of the universe back in time. This group's discovery of an accelerating universe was named Science Magazine's Breakthrough of the Year in 1998. Brian Schmidt joined the staff of the Australian National University in 1995 and was awarded the Australian government's inaugural Malcolm McIntosh Award for Achievement in the Physical Sciences in 2000. The Australian Academy of Sciences Posey Medal in 2001, the Astronomical Society of India Vainubappu Medal in 2002, and an Australian Research Council Federation Fellowship in 2005. In 2006, Schmidt was jointly awarded the Shaw Prize for Astronomy and shared the 2007 Gruber Prize for Cosmology and 2014 Breakthrough Prize in Physics with his High Z SN Search team colleagues. For his work on the accelerating universe, Brian Schmidt was awarded the 2011 Nobel Prize in Physics, jointly with Adam Rees and Saul Perlmutter. He is a fellow of the Australian Academy of Science, the United States Academy of Science, Royal Society, foreign member of the Spanish Royal Academy of Sciences, and foreign member of the Indian Academy of Sciences. In 2013, he was made a Companion of the Order of Australia. Brian also runs My Penrai Vineyard and Winery, a 2.7-acre vineyard and a small winery in the Canberra districts, which produces the Pinot Noir. Okay, before we pass on the floor to Prof. Brian, I would like to request all participants to switch off your videos and make sure your mics are muted so as not to disturb the flow of the talk. Okay, if anyone wishes to ask anything, please do not interrupt Prof. Schmidt during his talk. It would be better if you type it at the chat box, or you could ask it at the end of the talk. Thank you. Prof. Schmidt will talk about the universe from beginning to end. Prof, before we begin our discussion, would you like to say anything?
No, I'll have a long time to talk with everyone, so look forward to it, and hope everyone's ready to find out at least what we think we know about the universe.
Okay, Prof, before we begin, I just noticed that you were raised in Montana. How come you did not move into paleontology?
Well, I was interested in paleontology because we have, for those listeners who don't know, a lot of like the T-Rexes in the
Yes.
world Triceratops are all discovered in eastern Montana where my mother grew up. And so I used to go fossick for fossils as a kid. And yeah, I don't know. Something I could have done. One of the beautiful things of being a scientist is science. There are so many interesting things to do in science. It's sort of like going to the buffet that has too many things to eat. And so you have to make choices. And, I made the choice of astronomy rather than paleontology.
Okay, the floor is yours, Prof.
Thank you. All right. Can we confirm that everyone can see my slide?
Yes.
All right. Excellent. So today I want to talk about the universe from beginning to end. And this is a story of all that we know about the universe, and also talk about some of the things maybe we don't yet know towards the end. And it is an amazing thing that humanity has been able to piece this together, this story together, obviously going back 60, 70, 80,000 years ago, but huge amounts of work done in the last 300 or 400 years, and especially the last 100 years. So let's start with the beginning. And so the rise of the universe, long ago, long before stars and galaxies, something happened. The universe as we know it was created, and it was expanding in all directions. It was very hot, it was dense, and as it expanded, it cooled. And we call this time the Big Bang. We don't actually know what the Big Bang is in detail. We know what happened after the Big Bang. So the Big Bang remains a bit of a mystery. And we see its afterglow in what we call the cosmic microwave background. And this is a picture of the cosmic microwave background. It was discovered in 1964 accidentally as sort of noise. It turns out it is the picture of the whole sky. So this is an image taken with the Planck telescope. And this image is taken in microwaves, the same
Brian,
frequency of light that we use to cook vegetables if you have a
Brian,
microwave.
Brian,
Yes.
I think you're not on full screen because we could see your next slide and all that.
So we've kind of switched around.
Okay.
Let me try this. Maybe if I haven't crashed my.
Okay.
So,
Yep. Okay.
yep.
Yeah. Cool. Nice. Thank you.
Okay. Sorry. Thank you very much. The cosmic microwave background uh, is when the universe was glowing after the Big Bang. And we'll talk about it later on. But the universe here is about 3,000 degrees Celsius. So very similar to the sun. It's a little cooler than the sun. And it is at a time when the universe was cooling. And at this period, the universe grabbed its electrons, okay? Because hydrogen, when it's hotter than 3,000 degrees, the electron is stripped away from it. And so we say the universe is ionized. Then electrons scatter light, which means it's like a giant fog bank before, when the universe was hotter than 3,000 degrees. When it cooled to 3,000 degrees as it expanded, the universe suddenly, each hydrogen atom grabbed its electron and the fog bank lifts. And we look back, and this is essentially the fog bank of the universe as we see it. And you see these little bumps and wiggles. Well, those are little bumps and wiggles in the universe formed, as we believe, directly, literally right at the time after the Big Bang. And they give us a way of understanding the universe, which I'll talk about later. But this is one of the reasons we believe a Big Bang happened, because it's kind of hard to understand how what we see here could exist in any other way. So since that time, this image, as I'll show you, is many, many billions of years in the past. And light from this traveled all that time to reach us. So how do we actually know all this? Well, we really start with Edwin Hubble. Edwin Hubble had access to the Hooker 100-inch telescope, the largest telescope on the planet, for many, many years, located just outside of Los Angeles at Mount Wilson. He was an astronomer who was looking at little fuzzy things called galaxies. And we learned in the fullness of time that these objects were very distant. They were well outside of our galaxy. And so everyone else who was looking at stars or looking at things normally hundreds, if not thousands of times closer. And what Edwin Hubble did is he looked at these fuzzy galaxies and started with this telescope. As it got better and better run, he was able to start picking out individual stars in these galaxies. And we have the notion of what we call the inverse square law in physics. The further away an object is, the fainter it appears. And so by looking at how bright a star is, you can judge its distance. The further it is away, the fainter it appears. Now, you do have to make a few assumptions that these stars, that you're looking at the same types of stars, and that turns out to be very difficult. And Edwin Hubble didn't do a great job at that, but he did a good enough job. And he, as I'll show you in just a second, made a very famous diagram called the Hubble, which allowed him to uncover Hubble's law. So distance is easily measured from the brightness of an object if you have the same type of object. The other thing we have is the notion of velocity. So a galaxy, if it is moving away from it, its light from its stars will be stretched by the Doppler shift. Its motion stretches the light. If it was coming towards us, the light would be compressed. And when you stretch light, that makes light redder and moves, for example, each photon to a slightly redder color. And so we in astronomy can actually measure essentially the color of the light. And we can do that very accurately, it turns out, because each element has a fingerprint of colors, and those get shifted back and forth depending on whether or not an object is moving towards us or away from us. And Vesto Melvin Slipher in Arizona at about this time, a little before Hubble, had actually gone out and made a remarkable discovery, which was when he looked at these fuzzy objects we now call galaxies, essentially every single one of them seemed to be moving away from us. And in a universe that's random, you would expect some coming towards us and some moving away. So it was like they were trying to move away from us. This is a real mystery. And Hubble, by creating this diagram, solved that mystery. He plotted brighter stars versus fainter stars, or close objects, distant objects. That's across the x-axis. And on the y-axis, we could look at Slipher's measurement of what we call redshift or velocity. And so it turns out the further an object is away, the faster it's moving away from us. And from this data, Hubble announced to the world that that meant that the universe was expanding. Now, here's the universe, and I've just expanded it. Okay, you can see I went through and took a cartoon of the universe and I expanded it. And I want to just overlay before and after and see what we see. So I took the first image and the second image, I overlaid them. And what you can see is in a universe that's magnified, nearby objects have only moved a little bit, and distant objects, they have moved a lot. And so if you think through it, like this cartoon shows you, if the universe is expanding, then nearby objects, as it expands, move a little bit during a period of time. They have a low velocity. And distant objects, well, they're pushed a lot further away from us, and so they'd be moving fast. So you literally have a universe that is expanding. Now let's think about a universe that's expanding. Get a cartoon, a universe is expanding. Let's think about what happens when we go back in time. As we go back in time, then things will be closer and closer and closer and closer, and eventually everything will be on top of everything else, and you naturally get a time like the Big Bang. It doesn't tell us why the Big Bang occurred, but it tells us if we see an expanding universe, the natural thing is for the universe to have started as a very dense time. And when you compress things, it's hot. So it's kind of a natural thing, like a Big Bang, that you expect in an expanding universe. Now, let's graphically think about this. If I have two galaxies moving apart over time, like this diagram shows, then that dotted line is the trajectory in how far apart they are as a function of time. That dotted line turns out to be what we call the Hubble constant, or the rate that the universe is expanding. So the slope of that line is an object's distance divided by its velocity. And that is what we call Hubble's constant, the expansion rate of the universe. So if I can measure how fast the universe is expanding, that is an object's distance divided by its velocity, then I can run the universe in reverse, and I can figure out when that arrow is where the two objects are on top of each other. That is, I can figure out how far back in time that is. I can measure how old the universe is since the Big Bang. Conceptually, very simple. I thought that was such a good idea that I did it for my PhD thesis back when I was a student at Harvard. And here I am showing Bob Kirshner 3 years, 11 days, 11 months and 4 days after I started my PhD thesis, my measurement of distances and recession velocities, redshifts, that allows us to measure the Hubble constant. And so Bob Kirshner, looking on, is very approving of the number that I got, which was a Hubble constant of about 70, and this was in 1993, which indicated the universe was about 14 billion years of age. So it turns out that was part of a conversation that was happening in 1993. The number that we think the Hubble constant is about 70. And so I more or less got the right answer, but we used the Hubble Space Telescope to go in and really refine the measurement and make it beyond a reasonable doubt. And so that was things that the director of Mount Stromlo, Jeremy Mould, helped lead with the Hubble Space Telescope, and one of the reasons I came to Australia all those years ago, back in 1994. So I've given you cartoons so far, but we actually have a theory. And the theory is Einstein's theory of gravity, known as general relativity. And it comes from Einstein having a profound thought in 1907 that acceleration and gravity were interchangeable. They were equivalent, known as the equivalence principle. And nominally, he had this idea, or maybe apocryphally would be a better way to say, had this idea when Einstein saw someone falling off the roof of a house, presumably to their demise, and he thought, rather than maybe calling an ambulance like a normal person would do, I don't think that person feels any gravity as they fall. They feel weightlessness. And that's because the acceleration and the gravity they feel would be counteracted. And he thought, I think that must always be true. They must always be interchangeable. So a small little thought that took him 8 years to solve. And it essentially says, if I put you in a rocket and I accelerate at 9.8 meters per second squared, I cannot tell that that is different in any physical way from just sitting in a box on planet Earth and being accelerated by 9.8 meters per second squared. But when you reconcile this, it turns out you get very complicated equations of how time and space are related. And space is going to be curved to make it possible. The only way Einstein could make this work is if space itself is curved. And so this turns out to have been a huge announcement in 1915, people were very skeptical of it because he did it on aesthetic grounds only. But it made predictions. It made predictions that the anomaly in Mercury's orbit that had been known for 100 years, because Mercury doesn't quite orbit the sun the way Newton's law says, small but measurable. It actually predicted why that occurred due to this. It also predicted that space was curved, so that, for example, if you looked at an eclipse, you could go through and you would see when the sun was in front of stars during an eclipse, the positions of the stars would be distorted in a calculable way. And then when the sun moved on, and you could look at those stars when the sun had moved on, then those stars would be in different positions. And that is what was seen in 1919. And so when these observations were made and showed that Einstein, from that pure aesthetic thought alone, had revolutionized Newton's laws of gravity, that is what made Einstein a household name. Now, Einstein was already one of the most famous physicists, but physicists are typically not household names. Einstein had done something that almost no one else in history had done before or has done since. He has created a theory that seems to describe the universe and has lasted now 100 years without a blemish from pure thought alone. The only other person who can really, you can say, who's done this, I think, is Copernicus. Copernicus overturned the idea that the Earth was the center of the universe, making a prediction the sun was at the center, not because he was trying to solve a problem, but because aesthetically it was a simpler idea. And it turns out it, of course, was correct. So it's very rare for that to occur. Normally, discoveries in science are made because there is a problem we're trying to fix, a place where our theory does not predict the correct answer that we see in life. Copernicus and then Einstein famously came up with a theory just because they thought it seemed like a simpler, beautiful way to describe the universe. So this theory allowed Einstein to do many, many things and everyone else. It allowed Einstein to do what Newton could never do, which was to solve cosmology. So Newton tried to understand how the universe would work in his theory of gravity. So imagine a universe without end. And if you try to solve that problem with Newton's laws of gravity, it turns out there's only one solution. And that solution is the universe has nothing in it. Anytime there's anything in the universe that doesn't make sense, there's no solution to Newton's laws. So Newton realized that was a problem, and he could never solve it in his life. And as someone who, and it really, I think, weighed heavily on Newton's mind, in the same way, actually, Einstein wanted a theory of everything and never could crack that or even really come close to it. And that weighed heavily on Einstein's mind through his career. So Einstein could go through and use his equations, it turns out, and solve cosmology, but they gave a funny answer. The solutions were dynamic. The universe needed to be in motion. Now, he looked around in 1915 when he did this, or 1916, and said, the universe seems static. And he looked, therefore, very carefully at his equations, and he realized he had not included absolutely everything in them that he needed to. There could be a term he called the cosmological constant that is essentially meaning space has energy. And this energy, when it interacts with his equations, causes gravity to push rather than pull. And he thought if it was the right amount, it could offset the gravity of everything else in the universe and make the universe static. Now, it turns out it doesn't work because the universe would be put in, it suffers from the butterfly effect, that any small perturbation anywhere in the universe would set the universe in motion. So it didn't actually solve the problem. And later on, Einstein stuck with this idea for 15 years and eventually gave up with it when it was realized in 1929 the universe really was expanding. And he described himself as acting like a donkey later on in life for being stubborn and sticking with an idea that was wrong. So, new, the Einstein's laws give us a slightly different set of predictions, or maybe a fuller set of predictions. So this is the diagram I showed you just as a cartoon. If the universe is expanding, then two galaxies follow that trajectory. And that turns out in Einstein's universe to be true if the universe is empty. If it literally has nothing in it or tiny amounts of stuff in it, then the gravity of the universe will attract things, but there isn't any of it, so effectively has no effect, and the universe just expands by the dotted line. But if the universe has a lot of stuff in it, so it has a higher density than being close to empty, then gravity will slow the universe down. The expansion of the universe is slowed down by everything attracting everything else. And so the heavier the universe is, or the denser the universe is, the faster it would slow down. And so the universe would actually not quite be as old as you would otherwise think. So, for example, for a very reasonable amount of material in the universe that we thought when, for example, I made my measurement in 1993 of the Hubble constant, the universe might be between 10 and 13 billion years old rather than the 14 billion years old I measured. Now, 13 was sort of okay, but 10 was not okay because we thought we knew of stars that were at least 12 billion years old already existing in the universe, and we didn't want the universe to be older than the stuff, the universe being younger than the stuff that's in it. That would be a real problem. And that 11 or 10 billion year old universe was the preferred model of theorists. They thought the universe had to have a lot of stuff in it for ways to understand the Big Bang I'm not going to talk too much about, but effectively to understand those bumps and wiggles in the early universe, the theorist would say the universe needs to actually have a certain amount of stuff in it such that it should, they thought, slow down over time. We'll talk a bit about that in a sec. So that's the prediction of general relativity, and it makes predictions of the future. So if the universe is light, then it keeps expanding by the dotted line forever and ever. If the universe is heavy, then the universe would slow down, stop expanding, and go in reverse. All universes begin a Big Bang, but only the heavy ones end in the Ganab-Gib, the Big Bang in reverse. So what would we do with this? Well, we can go out and think about some of the other ramifications. I told you that the universe in space can be curved in general relativity. Well, if the universe is heavy, it curves space. So if the universe has a certain amount of material, like a lot of material, it bends space into a sphere. So that in the finite heavy universe, so this is a universe that is very dense, then the universe ends in a Big Bang in reverse, the Ganab-Gib. So that's a heavy universe. It's finite in time. But it turns out it also bends on itself in 4 dimensions. I'm only kind of showing you 3 on 2 here. Bends onto itself such that if I were to head out that way in the universe, given enough time, I would eventually come back to where I started. Just like if you go around the Earth, it's bent in a way that's not obvious just by looking out your window. A light universe, turns out space is naturally springy, and it has the shape of a saddle or hyperbolic geometry. In this universe, if you make giant triangles, they add up to less than 180 degrees. In the heavy universe, just like on Earth, the triangles add up to more than 180 degrees. And if you don't believe the triangles add up to more than 180 degrees on Earth, Don't do one on a piece of paper. That's just a tiny little piece of Earth. Get to a globe and put 3 points in and look at what the triangle looks like. It adds up to more than 180 degrees. And then there's the just right universe. It turns out this just right universe has just enough stuff to bend the universe away from springiness so that it doesn't actually curve onto itself. It just goes flat. Triangles add up to 180 degrees. And to understand the very early universe, theorists like a universe that has this amount of stuff. And that's quite a bit of stuff. This is a universe that, as it slows down to rest in infinite time in the future. So it does go on for infinity in time, just as it goes on to infinity in space. But it is a universe that theorists like to understand the early universe. Now, it doesn't mean the theorists are right. They're often right, but it's something you want to go out and test. And how might we test it? Well, it turns out if the universe is slowing down, we have the opportunity to look back into the universe's past because light travels 300,000 kilometers per second, which means if I look far enough away, light takes, in some cases, billions of years to reach us. So imagine I could measure distance and I could measure redshift or velocity, not for objects just in the nearby universe, but I can look billions of years in the past and make the same measurement. I could then measure how fast the universe was expanding now and compare it to the past. If the universe is light, then nothing's going to change. The universe will be expanding the same speed in the past as present. If the universe is heavy, heavier than that magic just right point, then gravity will win and the universe will be slowing down faster than that dotted yellow line. And we'll know that we have a heavy, finite universe that will end in the future in a Gnab Gib. If the universe is slowing down slower than that dotted line, then we know that gravity is going to lose. The universe is going to continue to expand forever. That seemed to me like a very good experiment to do in 1994 when two major breakthroughs occurred in our field. One conceptual, one technical. So the first conceptual, I worked with many astronomers down in Chile, and they had discovered by making very careful observations in the early 1990s that a certain type of exploding star called Type 1a supernovae that take about 20 days to rise and fall could be used to measure very accurate distances. Distances as accurate as about 6 or 7% per object. Now, that doesn't sound super accurate here on Earth, but in astronomy, this was unprecedented. It was by far and away the most accurate way to measure distances. And these things are bright. They're 5 billion times brighter than our sun. And so they end up actually creating most of the iron in the universe. And because they're so bright, I could see them all the way across the universe, probably with technology, as I'll show you, out to 8 to 10 billion years into the past. So that was a conceptual breakthrough by my colleagues in Chile. And then the technical breakthrough were digital cameras. So digital cameras, which we're all used to now in our mobile phones, well, those, of course, were created in the United States, it turns out, for military applications, but they were adopted by astronomers almost immediately and scaled up, and we really helped drive this technology. And so in 1994, we started getting large digital cameras, similar to what we're used to now. So we started getting 4 megapixel cameras in 1994, and a 4 million pixel camera was big enough that we could discover on large telescopes Type 1a supernovae. These are 100 times more sensitive than photographic plates that we used before. And 4 megapixels meant we could see enough galaxies to have the hope of discovering one of these distant supernovae, because supernovae, it turns out, are very rare. The last one we know of in our own Milky Way was observed by Galileo in 1604, discovered by Kepler, maybe not, certainly cataloged by Kepler and Galileo, 1604. So it's 400 years plus since we've had a Type 1a supernova in our galaxy. So it turns out if you look at tens of thousands of galaxies, then you have a hope of discovering these. And so the digital cameras we employed during this time, and here's what an image looks like. In a night, we would be able to take 1,500 images like the one I show you here. Each one contains several thousand galaxies. And therefore, by taking an image before and after, we could discover an object like this one. Now, this object, it's a galaxy with a little star next to it, but we know that's a supernova because we took an image 3 weeks earlier and nothing became something. And so this object turns out to have been 5 billion light years in distance. So it exploded 5 billion years ago before the Earth was formed. That's the power of cosmology and our instrumentations we have these days. And so we could go in and use a whole bunch of software that I was responsible for writing to identify about 3 of these in those 1,500 images. And I'm going to bring you to a movie that we took during this time. We were doing this work in Chile at the Series-24 4-meter telescope. It has the driest, clearest conditions anywhere in the world. There's Nick Sunsef, who helped founded the team. He was one of those Chileans who figured out the Type 1a supernova could be measured, useful for measuring distances. Now, we only get 6 nights a year. And that's as much time as anyone gets anywhere. And so we've got to be making sure the data that's being taken is perfect. And then we put it down on all sorts of telescopes. It was 50 gigabytes of data, which was a huge amount of data. I was using early AI algorithms. But of course, we had to use a whole bunch of astronomers go through and make sure my software, which wasn't that good, actually discovered things we needed. And time was of the essence because we needed to get a spectrum. That's the colors of the rainbow, so we could identify the object as a supernova and measure its redshift, its recession velocity. So there we're using the largest telescope in the world at the time, even today, Keck, up in Hawaii. We had this time pre-scheduled, Adam Rees, Alex Filippenko there, going through and taking our objects. So this was an incredibly onerous task back because the telescopes could take a lot of data, 50 gigabytes a night. And this is at a time when the largest hard drives we had were 1 gigabyte, and the computers were much slower than my iPhone is now. So I would literally piece together every computer that we had at the observatory to run this software. We would discover 5 objects a year, maybe 10 when we got better at it. And so in 1998, after 3 years of work, we had our first big results, and this is what they looked like. So across the y-axis, this is the redshift. This is how much the objects are receding from us, made from the spectrum. And then we have each object measures the distance by velocity, measures essentially the expansion rate relative to the current one. And so each object has uncertainty. So they're error bars. And so we're sure 2/3 of the time the answer should lie within those error bars. And what you can see is the nearby objects, and these were largely done by my colleagues in Chile, although the group at Harvard did contribute some as well. If you compare those nearby objects to the distant objects, you can see those distant objects, not a single one, even with the error bars, is consistent with the bottom part of the diagram where gravity wins and the universe eventually collapses. Now, I was kind of sad because I kind of like that idea. The universe has a beginning and an end. But more interestingly is on average, those objects lie above the yellow part of the diagram where the universe is slowing down over time. Instead, they lie above the diagram where the universe was speeding up. And so it is this diagram that led us to win the Nobel Prize in 2011, where the universe is speeding up over time. I should say, this diagram, like Hubble's, is a little messy, but we were 99.95% sure that the universe was speeding up. Another team that was competing with us, working using a very similar set of techniques and they had developed some of the techniques themselves, out of Berkeley, ended up at the same time arriving to the same conclusion, so that together we were 99.995% sure. And we were jointly awarded the Nobel Prize in 2011, and here we all are in Stockholm. So please remember, it was a team effort. I, Adam, and Saul Perlmutter obviously won the Nobel Prize. We get a lot of accolades and attention, but I really need to emphasize this was the work of two teams with many, many people, all who put their heart and soul into this measurement. Now, how do we understand the universe speeding up? Well, Albert Einstein, that thing where he thought he was acting like a donkey, well, it turns out we need it again. In Einstein's theory of general relativity, the cosmological constant can cause the universe to actually accelerate. It makes gravity push rather than pull. Now, we're not absolutely positive it's the cosmological constant as Einstein suggested. It might be something that changes over time. So we give it a generic term called dark energy. So that is the seeming solution, but there's a kick. It does make some new predictions. Einstein's theory of general relativity, if I put the trajectory of the universe, it looks like this. The universe, it turns out, has a different curve, and in the future, the acceleration is predicted to become faster and faster and faster and faster. And we'll talk about the implications of what that means at the end of my talk. But in the past, it turns out we have an interesting trajectory where the universe is does this weird curve. And I think it's worthwhile understanding why that occurs. Dark energy is part of space itself. As the universe expands, it doesn't change. We, on the other hand, well, as the universe gets bigger, we don't change. We don't expand with the universe. Our fundamental forces keep us together. Our density stays the same. And so as the universe doubles in size, the density drops over time of material like us. So right now, it would seem that the universe is full of dark energy. Turns out we need 70% of the universe to be dark energy right now to explain what we see. But in the past, when the universe was smaller, there would have been less dark energy relative to what we are, because its density stays the same and our density gets larger as the universe gets smaller. So what the prediction is we go back 10 billion years into the past, actually dark energy would have been very small amount of the universe, and the universe would have been slowing down. So the trajectory shows the universe here slowing down, and then about 6 billion years ago, speeding up. It's kind of a crazy universe, but it seems to make predictions we can go out and test. So the detailed analysis is that the universe needs to be a mix of normal gravitating matter pulling on the universe, about 30% of the universe, and 70% of the universe pushing the universe apart. That's the prediction. Now, when we made this announcement of evidence that the universe was speeding up in 1998, I'll be honest, we couldn't make head nor tail of it. It seemed crazy to us, and we expected people to be highly skeptical because it's a crazy result. And so we needed to go out and immediately start making measurements. And the cosmic microwave background has emerged as this amazing laboratory on the universe for making such measurements. Why? Because these little bumps and wiggles that you see there are actually sound waves left over from the Big Bang. And the sound waves we can understand here on Earth, the physics of very accurately, and although sound, we're often told there's no sound in space. Well, there is sound in space at low enough frequencies, like light year long sound waves. And so these sound waves here are light years, many, many thousands or millions of light years long. And they kind of create a splash mark, as I'll show you, that we can use physics to measure. And so here's how it works. Imagine you have a pool of water and a pool of honey. You throw a rock in it, the waves are different depending on what the pool is made out of. That is, the splash marks depend on what the universe is made out of. So the Big Bang was like throwing a whole bunch of different sized rocks in the pool. Those splash marks splash around, and then we can go through and look at what the universe's splash marks look like relative to our model of what those splash marks should look like and compare it to what the universe is made out of. So it turns out this is the predictions of the universe that is 70% this dark energy and 30% of gravitating matter, with a little caveat. So the sound waves here, it's a complicated curve, but essentially what we're measuring is how many bumps there are of different sizes. And you can see there are a lot of bumps that are about a degree across. And what you're seeing in this measurement, each little dot is a measurement of that previous image I showed you. And the curve is the theory here that we constructed on Earth. So they fit just beautiful, but only if there is something new in the universe that we've known about, it turns out, for almost 100 years. The notion of dark matter. So dark matter is something we've never managed to see here on Earth, but we see evidence of in space. Dark matter is material that has gravity, just like atoms, but it doesn't interact with itself or with anything else. It just goes right through the universe, or right through itself. And the only way it interacts is by gravity. So when two atoms, if I try to collide two atoms, they bounce. First, there's, it turns out, electromagnetism force, but there's also the strong force and the weak force. And these things are very strong, and they do not allow atoms to pass through each other. The weak force, turns out, isn't that strong. It's aptly named. And so a neutrino, which does not really interact by either electromagnetism or the strong force, actually can pass right through an atom. And neutrinos are passing through your body right now and right through Earth. So crazy things can exist in the universe. So we need 25% of the universe to be things like atoms, but without interacting. And that's how you get this curve. If you change that number to 24%, then the curve no longer fits. If I go through and get rid of dark matter, there's just no sensible way to fit the data. So that is a measurement, but it does, as I'll show you, also indicate a couple other things about the universe. So dark matter I've already discussed. It allows us to measure the shape of space. Why? Because when space is curved, it turns out it magnifies or demagnifies the images that we see back in time. So think of it like the backside of a spoon, if space is curved onto itself, that is, the universe is heavier than the just right amount of stuff, then things are going to be magnified. If universe is light, then the universe will be demagnified and things will look small. And if it's just right, then it'll have a specific size. Those sound waves will have a size when we look at them. Now, when we go through and we look at those sound waves, they are exactly what you expect for a universe that is just right. That is, we need to have to about 4 decimal places a universe that has exactly the critical amount of material in it to make space flat. Now, you might be thinking, whoa, I thought I told you that the universe was, accelerating. How does this all work? Well, it turns out the material that makes space flat or not is any type of material. So atoms are fine, dark matter is fine, dark energy is fine. They all contribute. Anything that is in the universe contributes to the geometry of space. And so if you go through then and reconcile that the space is flat, well, that means relative to a just right universe, we have 100% of the matter needed to make the universe just right. 25% dark matter from the cosmic microwave background, 5% atomic matter, and that leaves 70% mystery matter, the same mystery matter that we need to accelerate the universe. And it turns out that accelerating universe does affect those sound waves' size just a little bit, tiny amount, in a way that gives you the consistent answer that the universe seems to have accelerating mystery matter, like the matter that we discovered in 1998. So it all kind of fits together in a crazy way. The universe really is messy. However we look at it, their universe seems to be full of dark energy. 70% of the universe, that's stuff, gravity that pushes. 25% is dark matter, stuff that is invisible, that's pulling on the universe. And 5% are the atoms that we look at here on Earth. And so it is interesting to note that essentially every Nobel Prize ever given in physics is about the 5% of the universe that we see here on Earth, and 95% of the universe is stuff that is invisible to Earth. Now, you might be worried if you're going to be making up invisible matter, maybe we just don't know what we're doing. But I'll remind you that that curve with all those bumps and wiggles was predicted in advance of making the measurement. And without dark matter and without dark energy, it simply doesn't work. And so science is not about what you want, but what explains the universe we live in. And so to this date, this crazy model has been able to predict pretty much everything we have seen in the universe. And I'll talk just a few little caveats here that are beginning to emerge now. But there's some big questions. What is dark matter? Well, maybe dark matter is an undiscovered particle that, like a neutrino, does not interact with normal material at all, or very, very rarely. And what is dark energy? So, as indicated, dark matter could essentially be a undiscovered particle. And we see it, evidence of it, as I said, in galaxies and how things and bits of material collide. Here I show 2 clusters that have literally gone through each other, and we are able to measure the atoms in X-rays, and they're all smashed together and glowing brightly. And we're able to measure dark matter because it curves space and distorts the galaxies behind them. And so what we see is dark matter has passed right through as these clusters have literally merged and passed through each other, and the atoms have crashed together, just like you expect. So dark matter, well, our hope is that it really rarely interacts, just like a neutrino does. So you might manage making it in the Large Hadron Collider at CERN. In that case, you'd create it, and then it would just leave the detector, and you would be missing some mass in some of the interactions. At this point, nothing's been seen. You might detect it, and so we're putting huge vats of liquid xenon. So it's cooled xenon, which is an inert gas, And it turns out that if occasionally these things interact, it will make a little ping that we can detect. And as we've made these experiments last longer and longer with larger and larger amounts of xenon, at this point, we still haven't seen anything. And finally, you might see it astrophysically. If dark matter interacts, it might put out gamma rays or other things that we can detect astrophysically. And again, at this point, we haven't seen anything that seems to actually fit what dark matter is. So dark matter remains a mystery. Dark energy, well, this is really hard. It's part of space itself. And the only way we really know how to approach dark energy is to see if it gets created exactly as space is created as the universe expands. And so the question we can ask is, does the universe accelerate exactly like dark energy predicts? So we have to make really, really accurate measurements, it turns out, to do that. And we have done that. We collectively, not so much me, people around the world have gone through and created larger and larger collections of supernovae. And it turns out the most recent measurements published in the last few months are beginning to see perhaps a small little deviation in the diagram at a couple billion years ago. But at this point, I'm going to be honest, the deviation is just a hint and could easily go away. It's not what we would say robust at this point. But we're going to take more data and make more checks. We've also developed other ways of making measurements that are very accurate. And it's these sound waves again, because these sound waves, eventually, those bumps and wiggles become galaxies. And so when we look at those sound waves now, we can actually see the sound waves and how galaxies are distributed. And we have these huge surveys of tens of millions of galaxies now. And you can see that foam structure is actually included in that. Foam structure kind of comes from some of those sound waves. And so here is also some measurements made in the last several months. And the bump shows the giant peak of sound waves that we can see in different galaxies at different times back in the past. And it turns out, again, when we look at objects at maybe 3, 4, 5 billion years in the past, maybe there's a little deviation from the black solid line, which is the prediction of dark energy and dark matter only. Now, again, I would say I'm not yet convinced. I'm not saying it's wrong, but we are taking a whole bunch more data. We're going to take 10 times better data here in the next 5 to 10 years with upcoming missions such as Euclid and Vera Rubin. And the actual telescope projects here on the ground, DESI, will be taking a whole bunch of data as well. So there's a little hint of maybe an issue there, but I think even a bigger hint that maybe something's not quite right is work that my colleague Adam Rees has helped lead, where they have looked at the Hubble constant that we measure in the nearby universe. So how fast the universe is expanding just in the nearby universe. And then comparing to the Hubble constant that it turns out you can measure from the sound waves in the early universe. It turns out to understand those sound waves, you measure the Hubble constant then, and then you can use the very accurate model we have of the universe and take it to the present day, and you can say, how does the expansion rate of the universe compare? And it turns out the numbers disagree. They disagree by a fair bit. We're kind of 99.99% chance that there's a problem. Now, I would say people have taken a long time to believe the measurements that Adam and his team have made using nearby objects with the Hubble Space Telescope typically, and now the James Webb Space Telescope. The cosmic microwave background measurements look so good, it's kind of hard to imagine how they could be wrong, but we need to look at those carefully. But at this point, I think that I'm not absolutely sure, but I really think there is a discrepancy that somehow the universe as we see it in the cosmic microwave background, when we project it to the present, doesn't quite line up to the model. And so physics, is something that makes predictions. If your model is right, then it gets the answer exactly right. So that is the power of physics, but it also means it's very sensitive to being right. So perhaps there is a little problem. Now, the first thing you might think is, okay, if you just showed us that maybe there's a hint that the universe isn't quite expanding at the right rate back 4 or 5 billion years ago, maybe that's the difference. Well, it turns out not only does it not fix the problem, it actually makes this problem worse, not better. So that's a huge set of questions that we have to answer over the next decade. But there are all sorts of other really amazing questions we can answer. The James Webb Space Telescope and soon the Square Kilometer Array, a radio telescope, are looking at the universe very near to the time of the Big Bang, where the gas made in the Big Bang became the first stars and galaxies. And we are seeing galaxies that are literally only a couple 100 million years after the Big Bang. So way, way younger than anything else we've ever been able to see in the universe. We're also able to go through, and I should say, when we do those measurements, the universe seems to have formed stars and black holes much quicker than we would have expected. And we see things with black holes in all sorts of ways. In 2015, looking with a very precise, what we call interferometer, 2 of them in the United States, we were able to see gravitational waves where space literally goes caused by black holes merging many, many billions of light years away. And when they merge, they cause space to kind of do a little shimmer, a gravitational wave, predicted, it turns out, by Albert Einstein back in 1916, 1917. And we have been able, therefore, to measure lots of black holes. And it turns out there are many more of them, and they're much bigger than we were expecting. The universe seems to have a lot more black holes than we were expecting. And it's not just ones that are 100 or 200 times bigger than our sun. It's giant black holes. For example, this one seen in the nearby galaxy M87, where you can actually see a relativistic jet shooting out of it here with the Hubble Space Telescope. But when we look at this now with the most sensitive radio telescope arrays we have, what we call the Event Horizon Telescope, so it uses the radio telescopes the size of the entire Earth to look right in at the center of that galaxy, we actually see the shadow of a black hole. That hole is because light can't come to us from where the black hole is, and so it shadows the light. And that tells us there is a many billion times the mass of our sun black hole in the center of that galaxy. And evidence for these galaxies goes right back into those early images of the universe taken with the James Webb Space Telescope. So there's some mystery there we need to solve. And of course, there are other questions. With the new generation of telescope, the 30-meter telescopes, we're going to be able to look and see things like Earth's oxygen in extrasolar planets' atmospheres. And we do that because when a planet goes in front of its sun, and here's Venus right in the middle of this diagram, going in front of our sun when it transited the sun, you actually get a little ring. And the imprint of what Venus's atmosphere is made out of will be put into the spectrum, just like Earth's oxygen is put into that colors of the rainbow spectrum shown on the far right of this diagram that we take from Earth of when we look at the sun. So we're going to have the chance when planets go in front of their stars to use these giant telescopes to look for the fingerprints of chemistry of life. And that might be oxygen, might be hydrofluorocarbons, could be any number of things depending on what is going on in that planet. And that's going to happen in the next 10 or 15 years. The European Extremely Large Telescope is being rapidly built in Chile. The Giant Magellan Telescope has just got its go-ahead to do its final design. And so these things are on track for the next 5 to 10 years. And so these are huge telescopes, 10 times bigger than anything we have on the planet now, and they will be platforms for discovery for decades to come. Now, what are the things that politicians and members of the public come up and say, Brian, it's great that you do all this work, but why do we pay you to do it? And there are many reasons to do it. Part of it's curiosity, but it turns out we really pay for it because it's useful. So I want you to look at your phone. So here's my phone, an iPhone, and I want you to look at things my area of astroparticle physics has contributed. So Wi-Fi. Wi-Fi is a technology whose standards and ability to perform were developed here in Australia by radio astronomers looking for evaporating black holes. The GPS. Well, GPS is made possible by creating very precise atomic clocks that we use in astronomy and physics, being able to put them on satellites in space, and then using general relativity to go through and calculate positions very accurately. The touchscreen was developed at CERN as a way of making humans interact with the data more efficient, as was the World Wide Web. And finally, the CMOS camera, that digital camera that's ubiquitous that we all have now, that was developed for a mission to Jupiter. But that's not it. Basic science, like astronomy, but not just astronomy and the particle physics, has done all of these things that were necessary to contribute to the technology that allowed the iPhone to exist. So it turns out that the advance of technology needs basic science to create the ideas that revolutionize our understanding of the world and allow new ways to interact with the world to create things that are useful. You don't just invent things that you don't know. You invent things that you do know. And so you need to have a creative process which to create these things. So our future. Well, let's just stay to our solar system. Our sun has a nuclear reactor, which is getting more and more revved up over time. And in the next billion years or so, the sun will be probably 30% brighter than it is right now, and will start to evaporate our oceans. And eventually, when it starts burning helium, it's going to puff up and destroy the Earth. It will cook us, will probably be captured and orbit in and evaporated within the sun. That's billions of years from now. Remember, multicellular life has only existed on planet Earth for less than 1 billion years. So the problems with the sun happened far enough in the future, you don't need to have nightmares about it, but they are coming. But the future of the universe, well, the universe seems to be driven by dark energy, because the more that the universe expands, the more dark energy is able to dominate what's going on. So dark energy will be able to push the universe apart faster and faster over a time, according to general relativity. And eventually, the creation of space will happen more quickly than even light can travel through it. So galaxies we see today, the light they are putting towards us today will never reach us. The light tries to travel through space, Space is being created faster than light can travel through it, and the light gets stranded and stretched. So eventually, the light effectively is so stretched it's no longer visible, and it never ever reaches us. So the universe, unless something changes, and I have given you hints that maybe our answer and understanding of the universe is not perfect, but unless somehow dark energy rapidly disappears, the universe went at an ever increasing rate, expand, fade away, and leave cosmologists like myself in the future with nothing to look at. Thank you very much.
Thank you, Brian, for that illuminating speech. Uh, I can see you have left Montana, but Montana has not left you.
Right. Yes. I
The-
love
the-
Montana.
The universe, the space paleontology.
Yes.
Okay, all right, nice. There are a few questions asked on the chat box. Recent observation suggests that dark energy, cosmological constant, is not constant but evolving with time. What is the fate of the universe for evolving dark energy?
So the answer is I don't know. It really depends on how dark energy might evolve. If dark energy just disappears, then the universe will probably um, have it kind of the dark energy needs to turn sort of into something. So the opportunities for what the universe can do are kind of quasi-infinite. If it turns into, if somehow the dark energy turns into something heavy, maybe the universe could slow down enough and stop. I think the most likely answer would be that the universe would stop accelerating, but it would still keep getting bigger and bigger over time. And so that would mean the universe might exist forever, but we would not come out of contact with things in the way that we are now. I mean, already we are out of contact with things that we've seen in the past. We don't get those objects back unless the universe starts to slow down really quickly. But it's really difficult to make predictions about the future when you don't understand the dark energy. So the answer is I really don't know.
Okay, another one. Prof. Schmidt, some researchers in 23 proposed that dark energy might originate from black holes. How do you see this idea fitting with what we know about the accelerating universe?
So there are about 10,000 different proposals about how dark energy comes to be, this being one of them. So at some point, the question is, does it make sense as a way of having it? And does it make some predictions we can test? So at this point, I would say, depending on, there's actually many ways that people have proposed to have black holes do this. Some of these will actually fill the universe with radiation, and that radiation should be detectable, in which case we could check it. And the challenge we have right now is these black holes would have existed in the early universe, and maybe it would be a way to resolve the Hubble tension. That is the fact that the Hubble constant that we measure early and late don't seem to manage. The black holes that are in the universe right now are very big, and they don't evaporate slowly, so they won't really affect what happens next. But it could have affected the trajectory of the universe in the early universe, I think. And if there are other forms of black hole dark energy, I'd need to look at the details. As I said, there are many, many more theories than I can keep track of.
Okay. May I ask, could the theory of small things, quantum mechanics, ever be reconciled with theory of massive things, theory of general relativity? in your opinion, which current prediction could correlate these two theories? In effect, string theory, quantum gravity, etc.
Yeah, so the hope is that we can reconcile them, but Asman is absolutely right. We do not have anything that really reconciles them well at this point. String theory, M theory are two well-known, discussed ways that people have looked to bring them together. Uh, String theory has been very difficult to make predictions with. It's very complicated. It involves typically 10 or 11 dimensions. And at this point, it hasn't really been able to make any predictions that we can test it. But the idea is that we believe fundamentally the universe is a quantum, is bound by quantum mechanics, and gravity in this worldview emerges somehow by reconciling the complete theory of quantum, and that gravity as a quantum process would give you general relativity as a property. So one of the ways to look at the bumps and wiggles in the cosmic microwave background is to essentially look at how the bumps and wiggles correlate with polarization. And at this point, getting there, the problem is dust can kind of give a signal here, but quantum gravity is thought to be able to give you a signal that if you could see it, it would allow you to probe quantum gravity right at the time of the Big Bang, right after the Big Bang. So people are going through and looking very carefully at what are known as the B modes. Tensor modes is a complicated way that these things can be measured to see if we can see signs of quantum gravity. At this point, we had a very exciting announcement 7 or 8 years ago that turned out to be probably dust. And so we continue to make measurements. It's really
Okay.
hard.
Oh, yeah.
This is a place that I think some major theoretical break could occur, and dark energy is predicted by this theory. We're kind of stuck. String theory kind of has some nice bits, but clearly not the answer. But my sense is this is probably the right way forward, but I could be wrong. I'm worried that Prabha is
Lagging. Can you hear me, Brian? Yep, you're muted. You're muted.
I can hear you.
Okay. All right.
Yes, I froze up. Where did I freeze up in that answer?
No, I think your answer came through, but in bits and pieces. Okay. Never mind, Prof. We'll go through.
Okay.
We'll go through.
Yes, sorry. I'm gonna.
Yeah. Yeah. There's one by
Yep, go
Ganesh.
for it.
Yeah. Hello. Yeah. Yeah, Brian. You were saying something?
No? Can you hear me?
Okay.
Can you hear me?
Yep.
Okay.
Okay. Ganesh asks, Prof, what are the current update on WIMP, weakly interacting massive particles as a dark matter candidate?
So weakly interacting massive particles are one of the things that we're looking at in those big vats of xenon I referred to. And at this point, no sign of them. There's still some parameter space to go look for us. And I should say you can't do all WIMP particles, but you can do a lot of them with that experiment. At some point, we're going to start seeing neutrinos in those experiments, and then we won't be able to go anywhere because all you see is the neutrinos. You can't make heads or tails. There is an experiment that was done in Italy, also for a certain set of particles related potentially to WIMPs, that seems to show a signal that as the Earth goes around the sun, the signal goes up and down and up and down. And so we're building a replica here in Australia of that experiment because it turns out we should see the signal, if it's not due to the Earth's motion, potentially in a different way than they would see in Italy, where the original one is done. So that is one experiment I think most people are very skeptical of, that seems to show something, but we will see. It's a measurement we can make. There are other ways people are putting together to do dark matter experiments, but they are very challenging.
When you say xenon experiments, these are different from the heavy water experiments.
Yeah, so heavy water experiments are on deuterium. This is on xenon, and we use xenon inert, which means it doesn't have any chemistry. That we use a heavy one, then it's full of radioactivity. And so xenon turns out to have a big cross section, and you want it to be liquid for a variety of reasons that are useful, although it could be solid. But xenon is the heaviest non-radioactive thing that's chemically inert. That's why it's used.
Okay. Is there a more accurate version of or a successor of COBE?
Yeah, so COBE had WMAP and then Planck. So the data I showed you was from Planck experiment, and Planck has done the entire sky kind of as accurately as you can imagine. So there's no real advantage of doing any more experiments in space. What we're looking at now are arrays on the ground that look at very high spatial frequencies where radio interferometers can make the measurements here on Earth to arbitrarily good accuracy. We tend to stick them in Antarctica because it's dry there, or in the top of mountains in Chile. There are some issues around funding and access to the South Pole right now. So one of those experiments is on hold. And those experiments are also being used to do the polarization measurements I talked about to look for quantum gravity.
Just on an off note, Brian, when you make these computer simulations and measurements on space, do we assume is mostly hydrogen or a mix of elements? Right? I lagged.
All right, unfortunately, right now, but you'll need to repeat the question because I couldn't hear it.
Okay, all right. When we make these measurements and computer simulations on space, about space, do we assume a hydrogen universe, or do we assume a appropriately massed universe with all the elements right up to iron?
So when we make our simulations, we try to make the universe as realistic as possible. The early universe is hydrogen. Then we run it through cosmic nucleosynthesis, where you then convert about 25% of the hydrogen to helium, 24.5%, depending on the details, and trace amounts of lithium and beryllium and boron. And so that's sort of the cosmic microwave background. That's what the universe is made out of.
Okay.
And it turns out when we look at the most metal poor stars and galaxies, it is consistent with what I've just told you, that nucleosynthetic model looks correct. One of the reasons we believe the Big Bang. Then we need to wait for about 100 million years for stars to start to form. And then from then on, one of the things I try to measure is how the elements are formed in supernovae. And that information is fed into these giant simulations that use the biggest computers on the planet to run forth. And so we try to make it as consistent as we can.
Okay. There's a question by Neil Singh. Hello, Prof. Schmidt. One, what is your thought on conformal cyclic cosmology? Do you think there are Hawking points in the CMB? And two, is dark energy the quantum fluctuation in vacuum of space?
All right. So the first one is an alternative way of looking at the early universe. I would say it is an interesting area. It has some issues that it tends to um, have issues when we think about entropy in the universe that I don't want to go into that are complicated, but you might think you would get more and more entropy every time it did a cycle. And I would say that the ideas that in the cosmic microwave background that we see what's described here as Hawking points or circles or stuff, I think those are largely discredited, that we don't see them at this point. I'm not saying they're not there, but like anything, I would say at this point, there's no evidence to support this model. I wouldn't absolutely reject it, but at this point, I would go through and say most cosmologists prefer sort of the inflationary cosmology, but they just have to acknowledge we don't know what happens in the very early universe. This might be the right answer, but I would say there's no evidence for it to be correct. On the second one, is dark energy the quantum fluctuations of the vacuum of space? So the answer is I don't know. To give people some context to why that's an interesting question. In space, right now, right here, the Heisenberg uncertainty principle essentially allows fluctuations of objects where you get two sort of matter-antimatter particles, or two fluctuations to come together or to come apart and then come together in a very short period of time. So if I were to measure the energy of a piece of space at any given time, I have huge numbers of these little fluctuations occurring, and they should add up to energy. And since this is just a product of space, you could imagine having this energy everywhere in space, just like what the cosmological constant needs to be. The challenge is that if you go through and kind of use the universe and the laws of particle physics, you sort of have to go through and have fluctuations up to a certain energy scale. And when you add it all up, you end up with more than 50 orders of magnitude more energy than we seem to be observing. That is, if the universe had this feature of this being dark energy, we would have actually had dark energy take over right after the Big Bang. Atoms would have never formed, galaxies would have never formed, we wouldn't be here. So clearly there's something, if there's something making that stuff not work as dark energy. And at this point, there is not, in my opinion, a satisfactory understanding of why we don't have dark energy from those quantum fluctuations. That is an unresolved question in our universe.
Hey, on a side note, do experiments like gravity on LIGO and all that speak the same language with respect to dark matter, dark energy?
So LIGO, if you're going to be measuring, it's measuring black holes. So black holes don't have any volume, really. So there's no dark energy in them. Dark matter, they don't care. Dark matter, atoms, neutrinos, light,
Yeah.
it's all goes in there and does not come out separate through evaporation. So a black hole only has two parameters, its mass and its spin. So what it's made out of doesn't care. It's just its total mass, and everything can contribute to that mass except for dark energy, because dark energy is connected to space and can't be transformed.
Space. Okay. All right. Question by Paulus. Hello, Prof. Schmidt. Just a layman question. Is it possible for physical matter, dark matter, and dark energy to transform into one another in such a way that will accelerate the expansion of the universe? Please correct me if I'm wrong. Thanks a lot.
So it is possible for dark matter to transform, for example, into photons. Sorry, not dark matter. It is possible for physical matter, atoms. So if I have an electron and a positron, so that's the antimatter equivalent of an electron, if they come together, they annihilate each other and they put out two photons. And photons turn out cause the universe not to accelerate, they cause the universe to decelerate faster than atoms do. Okay? So it's pretty easy if we were to somehow annihilate all the stuff in the universe. Now, I have no easy way to do that. There is a question why all the matter in the universe didn't annihilate early on, because the equations of particle physics sort of indicate that for every electron, there should be an anti-electron. For every proton, there should be an anti-proton. And for some reason, there appears to be 1 part in a billion atoms left over. So most of the universe are photons, but 1 in a billion things in the universe is an atom. And we don't really understand why that occurred. That's a mystery as well that we don't understand. But converting to something that would make the universe accelerate, that requires a very exotic model. And, right now in Kamiokande, this giant vat of water that you talked about under the, in Japan, it's looking for example, proton decay. And it hasn't seen anything, despite having huge, many, many tons of water. So converting atoms to something else, dark energy, we just don't see any evidence of there any way to do that. So I would say really, really difficult to get acceleration. But it is possible to convert things through particle physics things, certainly of atoms, possibly of dark matter, although we can't even see dark matter interact at all right now. But maybe there's a way to convert it to radiation or to other things. But I would say dark energy, as we understand it right now, seems really difficult to convert to other things. It could be dark energy is an undiscovered particle that will effectively change state over time. But you can kind of make up, as a particle physicist, you can make up any theory you want of that type. So again, we just don't know.
Okay. I think the last 3 questions. Hi, Prof. Schmidt. Are there any recent developments in properties of dark matter and dark energy that could change our current theoretical picture of the universe?
I would say for dark matter, I've kind of told you what I know. We have an interesting theory that has emerged actually by a friend of mine who used to study supernovae, which is that if dark matter is an ultra light particle, then it turns out it has a wavelength, a quantum wavelength, which is the size of galaxies and clusters. And it would kind of give you a weird pattern in dark matter because of the quantum state. So this is known as fuzzy dark matter. So that's intriguing. I'm not sure if it's real, but it certainly would be intriguing. So that's kind of a new thing that's worthwhile looking at. Dark energy, I've told you, maybe there's some evidence that it's changing over time. So if that becomes more solid, that would change everything and give theorists a big chance to think about what could exist that would create dark energy, probably be a particle or a quantum type process that evolves over time.
Okay. I think the next question was already answered, and there's a curveball question. Could you share what it's been like to serve as Vice Chancellor while also being a Nobel laureate?
Well, becoming a vice chancellor, which is the president of the University, Australian National University, was an amazing job. It's a really hard job, but it's a place where you get a chance to influence society and, tens of thousands of students and try to make the world a better place by allowing thousands upon thousands of people to, build their potential, their human capital. So being a Nobel laureate is not necessarily the normal skill set for a vice chancellor, but it does, if you can manage the human side of it, it does give you a certain gravitas to go talk to politicians or, quite frankly, talk to faculty members and say, we need to do better. And so in that sense, it was very useful. So I'm very glad I did it for 8 years. But I will say after 8 years, I was exhausted and it was time for me to finish up and let someone else take the reins. So yeah.
That's a good one. Does it help attract students?
A little bit. But normally, students go to universities because the whole variety of factors. And
Yeah,
yeah, I would say more students are coming to ANU than when I started, but I probably wasn't the principal reason people chose ANU. It's a great university, and that's why people would choose it if it's the right place for them.
there's, there's, there's an even more curveball question there. Hi, Prof. I'm always curious on what type of view a Nobel Prize winning cosmologist has when it comes to existence of God. It would be nice to hear your view on it after so many years of experience studying the universe.
Yeah, so I'm not religious. I'm not anti-religious, so I don't consider myself an atheist who denies God. I am self-described as a militant agnostic. I don't know, and for me, I just don't care. It's not something that interests me. If it interests you or others, that's fine. Religion is very much about taking things on faith. Science is pretty much the opposite, where you assume everything we know is flawed in some way, and we try to make predictions and self-correct.
Yeah.
Are they exclusive? Nope.
Yeah.
If you have your faith bit, you go for faith. Many of my colleagues are religious, and it's fine. So to my mind, they're just very, very different, and they, at least in my universe, don't interact much. But as I said, I have no problem with religion as long as people don't try to tell me what I can and cannot do in my life based on their religion.
On that note, Brian, do religious cosmologists have a different worldview of cosmology? No, or
Not from
standard
my
physics?
experience. No.
So it's driven by physics.
They're always driven by physics. Yeah,
Okay.
I've never had one who they felt it was different. Their view is, you can always abstract God to say, well, God is, I am trying to understand God's work, and this is the way God is working. You can always have God be one step removed from what you're measuring.
Yeah. Okay.
Yep.
There's a question by Andy Steve. What are the things you look forward to teach with Paul Francis later in 26? As I believe he did say something about having an updated online course as continuity from ANU EDX.
Yes,
Oh,
so
actually, no, sorry,
we started a program called Mysteries of the Universe in 2014-15, which was one of the first big courses on edX when edX first came out. edX is kind of not going to be anymore. So our course, after 10 years and 440,000 people taking it, has finished up. So Paul and I are in the middle of building a studio and we're starting to re-record, updating everything. So our hope is to have a course, certainly for ANU students in early next year, and then our hope is to put it online. The course will, I think we envision it probably not to be free in the future, but scholarships available for people who cannot afford it. And hopefully it will be, a great update to the course. And I just find it amazing that we've had 440,000 people take a course. That is 3 times more graduates than Australian National University has had in its entire lifetime. So I think we have a lot, and we're going to add some interesting bits to it, where I'm hoping as part of the course, we're going to be able to interview the people who are making the discoveries as they make them, I mean, soon after. So it'll have a kind of a live astronomer part to it that you can really have a chat digitally like we're doing here with the people who make the discoveries with James Webb Space Telescope and get them online and have a chat as part of the program. So look out for it. Still got a bit of work to do to make it happen. There are a lot of work to do. And I'm unfortunately very busy. So I need to concentrate on getting it done between now and Christmas. And thank you, Paulus, for your comment. I tried my best, that's for sure. I didn't get everything right, but it wasn't for lack of trying.
Okay. All right. I think that's about it for us this time. Thank you very much for those for the temporal overview of space. Before we bid you farewell, we'd like to have a group photo with you. So I ask everyone to switch on your cameras. Yes, there's Nazri there. Paulus, thank you. Oh, and there's also an attendance link in the chat box if if anybody's interested. Okay, thank you all. Cameras, please. Sanjeevan, Chin.
I think you're going to go past Zoom's ability to, I don't think it can do 63 of us.
Different pages, I suppose. Faris is here. Thanks, man. Okay, everybody, smile, please. Next page, nobody is open. Dr. Osama. Okay. All right. Was this Shah? Are we done? Okay.
Done. Thank you.
Okay. All right. Done. All right. Then that's about it. So thank you, Prof. Brian Schmidt. We wish you a very good day, and thank you for that nice talk on cosmology, the beginning and end of space. We'll hope to have you some other time for some other dialogue series that we are conducting right now. Thank you then.
Yeah,
Have a
thank
good
you.
day.
Take care.
Have a good day.
Cheers.
Cheers.
Bye-bye.
Bye.